This is a reconstruction of the presentation made by Jim Cline in 2000 on his technical paper titled Kinetically Strengthened Transportation Structures. This was done in Albuquerque, New Mexico on February 28th, 2000. Here are some main graphics in the paper illustrating the principles involved of supporting the structure with internally developed centrifugal force as well as electrodynamic drag, and how it would cope with lateral forces on it, as well as an overall diagram which is in color here. A bit of background. This paper was a milestone that was reached. The presentation, the associated published technical paper, was a milestone for the KESTS concept. It followed over a dozen Genie library files, papers given to the Los Angeles chapter of the International Society of System Scientists, a RAND paper submission, Meditation Magazine published article, as well as a 1997 paper given to Space Studies Institute, but they had not published that. So this paper was deliberately made very simple in hopes that it would be accepted, and it was. Here's what the cover of the Space Conference proceedings looks like. And look inside the book at some pages with my graphics on it are shown here, including the overall KESTS diagram and the cross-section of the KESTS. And it's shown here by my hand. The presentation was done with view graphs back then. And I started off with some general concepts of explaining how air pressure stored within an inflated structure can strengthen and shape the structure, like inflated toys and balloons and fuel tanks. Can stored energy within a structure be used to straighten it and support the weight of a structure in a gravitational field? And specifically, can it support the immense weight of a transportation track connecting the surface of the Earth all the way up to geosynchronous Earth orbit? This is what we're going to look at now. Structures can be designed to utilize the stored energy within themselves to increase their ability to resist deformation from applied loads. This is already done in fuel tanks on large rockets. The stored energy within a structure can be three-dimensionally omnidirectional, such as in a balloon or a fuel tank, or it can also be two-dimensionally linearized, such as in a whirling rope lasso. The kinetic energy stored within the whirling circle of rope changes its shape from a limp clump of rope into a circular shape with the ability to resist deformation of its shape while it's spinning into a semi-rigid circular form. This shows similar forces, only first on the left we see a mass being whirled around on a string, and you see the forces there. And on the right, a very similar diagram, only this time the shape is constrained by a rim in which the object is rolling or sliding around. And the same forces are existed on the rim that had been done on the string before. Such a centrifugally stiffened semi-rigid circular form conceivably could encircle the Earth high in space, its angular velocity high enough to be at or above orbital velocity. And such a centrifugally stiffened semi-rigid circular form conceivably could also be offset elliptically, such that its low point could contact the Earth's surface and its high point reaching high above the Earth into space, such as up to the geostationary orbital altitude. If its internal circulating speed is higher than that required to remain in orbit, you will have a surplus outward force relative to the Earth. This upward force conceivably could be used to support a structure within which it slides, and it's attached to the Earth at its low point. What are we aiming at such a transportation structure? We know the enormous amount of energy consumed by rockets putting something in the geostationary Earth orbit right now. But the energy that's actually added to mass by moving it from the ground on the equator and putting it into a geostationary Earth orbit is actually very small. It's about 15 kilowatt hours per kilogram. That's all the energy that actually goes to the mass putting it there, and all the rest of the energy is fluff. It's wasted. So this transportation structure aims to go close to this theoretical value of energy required to move mass up into geostationary Earth orbit. By making the high velocity circulating mass be in the form of laterally coupled contra-rotating mass stream pairs, magnetically or electrostatically sliding on tracks within the geostationary structure, which is itself attached to the ground at its low point. There is a rising side of the circulating mass stream everywhere along the structure. By electromagnetically modulated the magnetic coupling between the rising mass and the track in which it slides, an additional upward lift force is generated on the geostationary structure. This electromagnetically coupled lift force could rapidly servo control the position of the structure in response to, say, winds and the changing live loads of spacecraft riding on it. Here's a simplistic illustration of how electrodynamic braking can exert a force on a track. At the top we see a locomotive traveling along a track, and then it applies its brakes, and there's a force on the tracks that's in the direction that the locomotive had been going. If the locomotive were going up, it would exert an upward force on the tracks. Another source of transportation and structural support energy could be from mass stream electromagnetic thrusters located in space on the structure below geostationary Earth orbit. These thrusters would balance their weight with the thrust it produces by pushing against the mass of the downward moving portions of the circulating mass streams, thus inputting kinetic energy to the circulating mass streams. These would be Earth synchronous solar electric power plants located below geo, and the downward thrust will add energy that can be taken out on the ground, thus delivering energy to the ground, as well as can be used to adjust the forces on the structure itself. Here's a diagram of the overall system. That's not the scale. The center is a representation of the Earth. The rim is the equator of the Earth. The black ellipse is the KEST structure, which has the armature sliding around in it and the spacecraft riding up and down it. And the outer ring is representation of the geostationary Earth orbit. The structure can be used to lift materials to build solar power satellites, and one of those can be moved over, beam energy down to power the mass stream thrusters on the Earth anchor point of the KESTS, thus powering the structure from solar power from then on. This shows a cross-section of the KESTS. The downward arrow points toward the center of the Earth, and the stator part of the structure is the sort of ellipse here, and the various mass streams are shown by rectangles along the edge of the structure, showing how they're laterally distributed. At the top we have the cargo carrying spacecraft vehicles, some going up and some going down. This shows another version of it where the There's extreme separation of some of the lateral thrusters so that they're off center, and when more dynamic braking is on, say, the lower left one, then it's going to produce more pressure in that direction, such as to compensate for wind loads that are blowing from that direction on the structure. Some milestones on the way to KESTS-GEO might be: first, build millimeter diameter KESTS to explore basic kinetically strengthened transportation structural concepts, to test the leading edge backward expulsion of mass stream elements for auto emplacement of KESTS, then build circular KESTS connecting mountain sites entirely around the globe along the equator, several hundred feet above sea level, to provide an alternate intercontinental transportation bridge and to get more experience. Then build KESTS to low Earth orbit using excess velocity of mass streams at its upper altitude to inductively couple electrical energy, which would be used to catapult payload to orbital velocity, something like Lofstrom's launch loop, and self-replacement of millimeter diameter KESTS-GEO structures all the way up to geostationary Earth orbit. This concept suggests an enormous space project, one that is far from the beaten track, a seemingly impossible project. However, if one stops laughing at it and starts seriously thinking about its technological challenges, mere problems to be solved, the potential to begin to appear is very worthy of effort. To fully use kinetically strengthened transportation structure concepts in an intelligent, cooperative way, there are many questions to be answered, designs to be made, mechanisms to be built and tested, structures to be built, conversions of worldwide corporate goals, and a world full of people to realize that we can all work together cooperatively to expand our civilization and do it in time to preserve our ecosystem. Thus the presentation was done. After 11 years of attempting to get formal awareness of my KESTS-GEO concept, including making a paper and presentation for the Space Studies Institute at Princeton in New Jersey in 1997 that they refused to publish. And here in this picture, I'm not quite believing that it finally is done. This photo made on a little Polaroid camera before the time of my digital cameras captures me as I return from making my formal presentation at the American Society of Civil Engineers Space 2000 conference in Albuquerque, New Mexico. Photo taken by my daughter, who was living there at the time. I'm holding a printout of my paper and a copy of the conference proceedings, in which the paper, Kinetically Strengthened Transportation Structures, was peer-reviewed and published.